on our second lecture of scanning electron microscopy, and I found this on the internet, and it's a company that's trying to sell this old instrument. And this is the same model I used when I was an undergraduate and also when I worked on my master's degree. And it's an older microscope, a scanning electron microscope made by a company called ISI, and it's an international scientific instrument. I do not think they are around anymore. But this is actually really, really cool. It even had an imaging system with this Polaroid system here where we would take pictures with Polaroids, and so it was very expensive to actually take a picture. Nowadays, it's pretty much like a digital camera. You can just snap away, so it's really kind of cool. This instrument here looks like it has interchangeable detectors. And so one of these is an older style backscatter electron detector, and it looks like you can just swap them out. And the detector would end up being right above the specimen, so that's how I kind of know it's a backscatter detector. And it's kind of a blurry image. It looks like it's on someone's driveway. This looks like a garage, so that's kind of interesting. But very, very old school. And individuals today using more modern equipment, I don't think realize how good they have it actually, but that's okay. Progress is good. I kind of like the giant console for just a few knobs kind of thing there. But an ISI, International Scientific Instrument, don't think it exists. There's kind of four main manufacturers of SEM now, and I've mentioned them before. Hitachi is a big one. Joel, Jeol, it's Japan Electron Optics Lab. That's another one. There is FEI, and FEI is Field Electron and Ion. They're actually owned by Philips. And the fourth one, excuse me, is Tescan, and they make kind of lower cost instruments. There used to be another company called Amray, and El Paso Natural Gas used to have an Amray. When I first started working for Intel, that was one of the first instruments I was responsible for. It was actually an Amray SEM, and they've since been bought by KLA-Tencor. They don't make standalone scanning electron microscopes anymore. They actually make automated instrumentation, and so inspection of semiconductor wafers is done on a fairly automated process. It used to be done pretty much exclusively optically. Now it's done using giant automated SEMs, and if I can find some imaging, I'll share those with you. It's actually kind of neat, automated SEM microscopy. If we take a look, so if you remember in the last lecture, I said that in all electron microscopes, the electrons are accelerated through a coil. Some of you have seen this instrument. Some of you may not have. It's used pretty widely in our failure analysis course. This is a Hitachi tabletop microscope. It's a TM1000. Hitachi did not invent the mini SEM, so to speak, or the tabletop grade SEM. It was actually ISI, which is this company here. They had them back in the 70s, actually, and small desktop model SEMs. And Hitachi didn't actually develop this for sale, really. It was meant to be taken to trade shows. And this is a TM1000. We'll talk a little bit more about detectors. This particular instrument only has a backscatter electron detector. It's a solid state backscatter detector, and you can kind of do some cooler things with solid state detectors that you can't do with the older style scintillator detectors. And we'll talk a little bit more about the differences between a solid state detector and a scintillating detector. But here it has a column. We can take this little skin off, and it has a column here. And you can adjust the electron gun so it points where it's supposed to. And you kind of see these baffles here for the, for the vacuum. There we go. Trying to catch my train of thought. In here is the electron gun, as I kind of mentioned before. You even have kind of the voltage warning there. You would unlock this little knob or unscrew this little knob, and the door kind of flips open. And this electron gun is very similar to the electron gun we have on our larger SU3500 SEM. Both of these instruments are thermionic instruments, and the S4800 is actually a field emission or cold cathode scanning electron microscope. We can kind of take a look. So here's the 3500. Let me change my pointer flavor to something that can click. And kind of a little tour. Again, you have the column and an electron gun very similar to what's in the smaller TM100 tabletop. We'll kind of take a little tour, and then let me turn the volume off. And this is an X-ray detector. It's actually a Peltier cooled X-ray detector, so a Peltier device like what you would find in a wine fridge. This is a proprietary detector. It's a UVD. It can be used at low vacuum. This is actually a STEM, scanning transmission electron microscopy. I can get transmitted images. I'm going a little too fast. I'm sorry. Let me kind of pause it. I forgot I'm doing a video within a video, so I can actually pause it. And I'm sorry for the angle. This is actually parallel to the ground, so sorry about that. This is a auxiliary unit. So I'll say this again. SEMS, so the basic unit of an SEM is basically just an electron gun shooting a beam of electrons onto a sample. And in this case, I have a holder that can take TDM-like specimens, and actually the same specimen you can throw in a TDM you can put in here, and transmit the beam through the specimen. Then I have a detector below it which can generate the image. And we'll talk a little bit more about scanning transmission electron microscopy later. But SEMs, you have 3 gun types, and we'll talk about the gun types today. But once you have an electron beam interaction, it's all about the different detectors that pick up the different signals. And so with this, I can actually get a transmitted signal, which is kind of cool if my specimen is thin enough. So that's the STEM. And again, it's another auxiliary unit. Back here, oops, I'm so sorry. Let me see, let me just get back to where I was. I'm sorry. I'll kind of do some real-time editing. There we go. Here, this is an old school photomultiplier tube, and we've already talked about photomultiplier tubes earlier when we talked about types of X-ray detectors, and I believe that was in XRD lecture 4. If not, it was 3. It was in one of the later XRD lectures. But this is a secondary electron detector. It's called an Everhart-Thornley detector. And I'll get the pointer. I'm unaware. I think maybe you can see my mouse when this finally records, but this is an Everhart-Thornley detector. It uses photomultiplier tube technology. There's a scintillator on the inside, which the secondary electron hits it, generates a photon with the scintillating material, which then gets converted into an electronic signal because that photon energy gets converted into an electronic signal through another device. And we'll show a schematic of scintillators again, and the whole cascading electron thing happens. Let me switch the pointer to not be a laser. And going around, I'm slow now, that's funny. Going around, we see the electronics here. So this little nub, if you will, is actually the electronics for the backscatter electron detector. So this also has a solid state backscatter electron detector, very similar to that tabletop. So the story of that tabletop model was that it was developed to be taken to trade shows like conferences and stuff like that, and they needed something portable. And they wanted to highlight 2 things, or maybe even 3 things. 1, the electron gun. 2, the backscatter detector at solid state. And 3, some people don't know this, this is actually a variable pressure SEM. So you can run it in, they call it charge suppression mode, but it's really a low vacuum mode. And what that means is you can put biological specimens in it, and wet specimens, semi-wet. Don't put anything soaking wet ever, but you can put like leaves in it, like organic material in it, and you can also put polymers in it. And usually, and we'll talk about this in a later lecture, When you have samples that don't conduct well, you get electron charging, so you have to coat it with gold or some other conductor. These SEMs aren't as sensitive to that, and this one has a charge suppression mode. This 3500 here has a variable pressure mode, so I can actually more discreetly control the vacuum. The tabletop has kind of quasi-high and then a low vacuum mode, so 2 modes. This is limited to 15 kilovolts of accelerating potential. This can go all the way up to 30, and I can actually, if I wanted to, I could discreetly control the accelerating voltage down to the fraction of a volt, actually. Oftentimes you don't. What else? So this has a manual tilt, but the X, Y, and rotation is all motorized. This can only go X and Y, and I think you can rotate with this one as well. I may be lying to you. How would it be X, Y if it's only one knob? So this only goes X and Y. Excuse me, watching my train of thought. At least I think I was right. This also has a Peltier EDS detector, and there's a special mount you're actually supposed to use when you do EDS measurements on this, and I need to try to get that and kind of show you all what that mount looks like. It's just an angled mount, and I have images of the inside. So we'll talk a little bit more about components of the SEM later. I'm actually getting a little bit ahead of myself. The goal of this lecture actually is to talk about types of electron guns, and so excuse me while I digress. If we look at this microscope, and someone was talking there, you might know who it was. Everhart Thornley detector. So this actually has 2 secondary detectors. What I'm going to kind of point out is this one is at an angle, and it's kind of high in the column area. And so this is called a semi-in lens detector. And Zeiss is another manufacturer of SEMs, and I forgot to mention them earlier. So we're mentioning all these manufacturers: Tescan, Joel, Hitachi, FEI, and Zeiss is another one. And they actually have done a lot of great work with putting their detectors in the column, so to speak. And where you find a lot of separation between manufacturers is they proprietarily put their detectors in prime locations. So they do a lot of research figuring out where the best amount of scatter happens, and they can place their lenses accordingly, or their detectors accordingly, excuse me. And Zeiss has kind of cornered the market, if you will, on in-lens technology. So they put their detectors actually back up in the column. And the analogy, if we go look at this one, is this is a fireplace, right? So your beam's hitting your specimen. Your specimen is like the chamber of a fireplace. And fireplaces are horribly inefficient because most of the heat goes, quote unquote, through the chimney. And so the idea of Zeiss's design is that the signal goes through the chimney, just like heat going through a fireplace. And so this is Hitachi's response to try to compete with Zeiss's in-lens technology. They put a secondary detector semi-in lens here. And so just kind of pointing that out. This is an objective aperture, so you have a variable objective aperture. Over here, if you can see it on the 3500, we also have a variable objective aperture. This one also has a condensing aperture, and I don't have a variable condensing aperture on my 35. The apertures are literally just small discs of metal with a hole in them. Okay, so I have a static condenser aperture here. The TM1000 has an objective aperture. I'm sorry, it's further down, an objective aperture and also a condenser aperture, but they're both static. You can't vary the apertures. You can take apart the optics assembly, and I've done that before, and replace the individual aperture actually, but that's another story. So if we go back and look at this, this has a different type of X-ray detector. So this is also an EDS detector. The one on the 35 is Peltier cooled. This is a liquid nitrogen cooled Peltier detector. Not Peltier detector, excuse me. It's a SILI detector. Excuse me. different types of detectors. Don't want to get them mixed up, especially when I'm giving an educational lecture. This uses a detector that's Peltier cooled. This uses a detector that is liquid nitrogen cooled. This is a SiLi detector, so silicon lithium detector. This is called a silicon drift detector, so it's solid state pretty much. A SiLi is almost kind of like a scintillator. We'll talk about it in a later lecture where we talk about the kind of the mechanics, if you will, of a detector. This little cylinder here is called the cold finger. So you can also fill this up with liquid nitrogen and get some higher mag imaging. And what the cold finger does for you is it limits thermal vibrations, basically. So you cool off your chamber, make it as cool as you possibly can, so you don't get phonons messing with your imaging. This has about 1 nanometer resolution. This is about 3 nanometer resolution. But there's a huge difference between 1 and 3 according to a microscope. So this is a much more expensive model. Granted, it's a little bit old, but it still has a higher resolution capability. What else do I wish to say? Field emission, cold cathode technology. You change the tip every decade. This is a thermionic, and it's like a light bulb filament, actually. And you can change it anywhere from 2 weeks to 6 months, depending on how much the filament's being used. Let's kind of carry on. See if I captured everything. So we already talked about the kind of the angled Everhart Thornley detector. Over here we have, I am so sorry. I'm embarrassing myself with my lack of ability to click. But hopefully you guys are kind of getting the picture of the detectors here. Pause. Okay. Here is another Everhart Thornley detector. It's another secondary electron detector. It's placed in a kind of a similar geometry as the secondary detector on the 3500. That angled detector, because of where it is, actually gets some backscattered electrons as well. And so you get some elemental contrast to that kind of higher angle detector. And we'll go back over here. This is an electron backscatter diffractometer. What this does is if you visualize how a backscatter electron occurs or happens, right? Your incoming electron comes in, goes around the nucleus, and comes out. So it's pretty much the same electron. It's a backscattered electron. If you think about that interacting with a lattice, you can actually tell crystallographic orientation. Okay, so you're going to have these electrons circling the nucleus of atoms that are arranged in a crystallographic or lattice structure. So you can actually tell crystallographic orientation with this diffractometer. This back here is a backscatter electron detector. It's not solid state. This is I believe it's a Robinson detector. I can't remember if it's Vivian. I think it's Vivian Robinson. I want to say she was an Australian scientist, or is an Australian scientist, who developed this. You have to insert it on this instrument. It is a scintillator device, so it's not solid state, but I've done head-to-head comparisons, and it actually images quite well. And so when I was learning about these types of scintillator detectors, I was taught that they were only for smooth metallographic-like specimens. But we did an experiment a while back, and we kind of did a head-to-head between a solid-state detector and this one, and found that we got really good imaging even for contoured surfaces with it. So always question what's told to you as fact, is kind of the moral of that story. And if you have the opportunity, test it out yourself. Don't ever be afraid to experiment. What else are we looking at? So I'm showing you a little bit more of this detector. And there's a piece of tape. There's a story. There is a professor. He's no longer part of the faculty. He's retired. I wanted to see if people were using it. So he would put a piece of tape on it, and then when it would rip, it would let him know basically that someone used it. It's like the old spy movies where someone puts a piece of tape on their door, and they come back and they see the tapes rip, so they know someone's gotten in their house. Here's kind of the business end of this microscope in all its glory. We see this column. You can kind of see these valves here. These are ion pumps, and we'll talk a little bit more about ion pumps. This is purely a rough pump turbomolecular pump system. It doesn't run at high of a vacuum as this instrument. This instrument, you need to use an airlock to exchange your specimen, so you only want to pump down and pump up a small area to the prescribed vacuum. And it takes a long time. It takes over a half hour to evacuate the whole chamber. And so if people lose specimens in it, it's kind of a pain. You have to evacuate the whole chamber. It takes a little while to change it out. This, you evacuate the whole chamber every time you swap out the specimen, because we're not running it as high of a vacuum. And so those are kind of some differences there between the two instruments. And again, accelerating electrons through a column. Here's the other column. Here's the column on the tabletop, and then this old school ISI had a column. And we'll talk about the columns a little bit more of microscopes, both of transmission and scanning electron microscopes. So I've flashed to this slide by accident several times already, but now we're finally ready to talk about it. Types of electron guns. I hope my image doesn't cut this off. Just so you know, I don't actually see my little box, so I kind of have an idea where it is, but I don't see it until I've already recorded the video, and I do kind of practice, so if I block out stuff, my apologies, it's kind of a mistake. So filament types, and I think I've told you the story of my former classmate who interviewed for a light bulb company, and in the interview he asked him what W meant, which is kind of funny. Tungsten. So tungsten, you can get coated filaments as well. There's still thermionic emissions, so Lab6 and cesium hexaboride, so lanthanum hexaboride and cesium hexaboride. Coated filaments, these types of filaments were, when I was a young student, were all the rage at the time and quite expensive. They've come down considerably in price. In my wildest dreams, I could go buy a hexaboride filament and just swap it out, put it in that tabletop, put it in the 3500, but you can't. Systems that use hexaboride filaments are specifically designed for hexaboride filaments, and they have to have a higher vacuum than a standard tungsten hairpin, so-called hairpin filament. Field emission is cold cathode technology. It uses tunneling, basically, to generate the electron beam, and I call it the second floor unit. But that's actually the 4800, so this second one here that we've seen. And then a Schottky emission electron gun. And I honestly don't see that many of these, but I know they're sold because I get catalogs of SEMs. It's kind of my hobby. So brightness is the key factor in the performance of an electron gun. So this is bright. These hexaborides are brighter. The field emission's brightest. And this is somewhere in between a thermionic and a field emission. I've looked up. There are some individuals that say this is the highest resolution, but I do believe that they are wrong. Field emission, to the best of my knowledge, gives you the best resolution in terms of electron microscopes, both scanning and transmission electron microscopes. And part of the reason is the emission of the electrons is actually cleaner, so to speak. So if you imagine, because this is field assisted, so Schottky is like thermionic, but you apply an external electric field. If you're generating everything cold cathode, right, you don't have the noise associated with the vibration of the atoms on the emitter. And that actually introduces a little bit of noise to your beam. And anyway, I'm digressing, but at least I'm digressing about what we're talking about. Electron guns, I borrowed this from these folks. I don't know why, actually, but it's kind of a hashing of what I've already talked about. And they borrowed this from a video game, and I don't know who owns that video game, right? So anyway, you better be careful there. Um, it says what I like to say, you want a lot of electrons in terms of the high current density. So in this case, beam current is amount of electrons basically, okay? And so higher beam current means more electrons. And so low beam current would be one finger tapping, medium beam current, maybe 10 fingers tapping, and high beam current 1,000 fingers tapping. Okay, so it's more. It's not quite the V equals IR Ohm's law kind of thing we tend to think about when we think of current, really. And so thermionic guns, they were the first. And if you think about a light bulb, the old school incandescent bulbs, and I oftentimes pass one around class, and I show you how if you look on an old incandescent bulb, you see it's been coated by the tungsten. Tungsten will evaporate, and it happens in an SCM as well, and that's why the filament eventually just burns out. It gets too thin to sustain the current. So field emission guns, so cold cathode is using a strong electric field. That's the basis behind field emission, and we'll take a look at the equations, kind of talking about these different things. And it's a single crystal of tungsten, so it's very similar to the old school probe microscopes, if you remember. Okay, so we talked early on in the class about probe microscopy. They had a single crystal tungsten that they etched to a thin tip. I'm telling you, the old school manufacturers for making these was literally to dip a wire in acid and let it drip down like a stalactite. I think the top ones were stalactites. Electron guns. So here is an example, and this is from this individual again. So Lab 6, it's single crystal, but it's coated. Tungsten wire is basically like a filament on a light bulb. And a field emission tip, it's a single crystal as well. Okay. This is a very big thing. Vacuum requirements are tougher for field emission guns. That's why our field emission scope has these so-called ion pumps, which pumps on the level of molecules, individual molecules of air. This is the filament that's used on both the tabletop SCM and the 3500. It's a filament, and it's specified in cartridge. So in the old days, this cartridge didn't come with the filaments, and it was a real bear that like just came out of hibernation and is trying to eat me bear to adjust the alignment of this beam, and it would take multiple days actually to change the filament on a thermionic. We have an older TEM that's thermionic. We don't use it anymore, and even that ISI, it was very hard to change the filaments. But now they're sold quote unquote pre-centered. I point out Ted Pella. There are multiple vendors for microscopy goods. Ted Pella is one of them. Another one is Electron Microscopy Sciences, EMS, and they've made a deal, I think, with one of the major scientific distributors. You can get them in Minor Mall. And then there's SPI, Structure Probe Incorporated. And there's pros and cons to each vendor. And it's more than just price, it's also the quality of the products they sell. Brightness. So we kind of talked about this. On my slide, brightness is the key factor in the performance of an electron gun. Brightness, so tungsten, it's pretty much the cheapest. Lab 6 is 10 times brighter than a tungsten filament, and field emission is 100 times brighter than a Lab 6 filament. Okay, so we're looking at a field emission being 1,000 times brighter than a tungsten. And so if you have the means to purchase one in the facilities to support it, you probably want to get a field emission, right? Well, think about it. Field emissions are also more sensitive to contamination, okay? So if you're doing a workhorse type of instrument, if you're working in kind of a dirty area, so if you have a SEM that's in a mill, like a steel mill or something that's a little bit harder to keep clean than a semiconductor clean room, maybe you want to go with a tungsten, even if you have unlimited funds, because you can actually get a lot out of a thermionic scope. So brightness, we'll talk a little bit more about beam geometry. I think I'm in need of a haircut. This is my quarantine due. It's been going on a long time, so it keeps getting in my eyes. So excuse me. Brightness, I've denoted it by beta, and the brightness is given by beam current, which really is the amount of electrons coming out of your emitter, divided by the cross-sectional area of the beam, multiplied by this solid angle. And a unit of solid angle is a steradian. So the unit of a linear angle, and we did this in XRD, so if I have between like 10 and 15 degrees, and I want to convert that to radians, I multiply that by pi over 180 and I get radians. Okay, so that's a kind of like a linear angle. A solid angle, like you see in a cone, okay, is a steradian, and astronomers use this unit quite often. So the unit of brightness is amps per meter squared steradian, and the brightness of a tungsten filament is roughly 10 to the 9 amps per meter squared steradian. And so we have 1,000 times more than that for a field emission filament. I may talk a little bit more about steradians later. So components of a SEM right in front of me, and I'm worried. I paused because I'm guessing that my face is cutting off part of this title. So components of an SEM. So the electron gun is what it says out here. And so this would be a thermionic gun. Brightness is current over, what did I say? I'm sorry. Cross-sectional area of the beam. That's dumb of me. Times the solid angle. And the solid angle is pi alpha naught squared. It's an area versus if it were just and 180 gets canceled out here somewhere. But if it were a straight angle, it would just be pi times your degrees, and there's a 180 in there somewhere that I believe gets canceled out. I need to revisit that. I'm sorry. I'm thinking out loud, recording it. It's never pretty. So this is a thermionic gun. This is a Wellnut cap, okay, aka the Wellnut cylinder, and we'll take a look at one very soon. This is negatively charged, okay. You have an accelerator anode, which is positively charged, and it sucks the electrons. These electrons are actually kind of coming off themselves. They're electron, they're thermionically emitted, excuse me, comes out of here, and it's actually shaped because the cap itself is negatively charged, so you're shaping the beam, and then you're accelerating it through your column, okay? That's how that's working. I'm looking at this. So tungsten versus a hexaboride. So Lab 6 cesium hexaboride. It's actually more than 2 times the cost of a tungsten filament. But the cost has come down. The thing is that I can't just buy one. I've kind of mentioned this before. I can't just buy one and plug it into my regular old tungsten filament. You need a higher vacuum. So you need a much higher vacuum than you have on our kind of lower vacuum instruments. It oxidizes much easier than the tungsten filament, which is why you need the higher vacuum. And it also takes a while to warm up and start emitting electrons. A field emission gun, so this is cold cathode technology. You have your single crystal tungsten. You apply an electric field, and the electrons kind of build up on your crystal. They're sucked off by this first anode, so you have to use an anode to actually get them to leave. And you have another anode, an accelerator anode, that's also positively charged. So you have a double set of anodes to kind of throw these, get them off the filament and throw them down the column. And this is kind of the big thing. So they're tunneling to this first anode, so they're overcoming the energy barrier, which is just free space and no heat. So this is cold cathode technology. If you're reading through a catalog, because SEMS aren't the only thing that uses quote unquote cold cathode technology, if you're reading through any electronic device, whether it's a sputter coder or another microscope, and I'm trying to think of something else that would use it, maybe even like a display for a television, and you read the term cold cathode technology, that's what it means, field emission. A Schottky emitter, it looks very similar, but the filament is heated up, and then you have the double set of anodes. So you basically have a thermionic-like filament, but you have a field emission-like accelerator anode assembly is the kind of the punchline for a Schottky instrument. The literature I found kind of shows that they're oriented differently. So 310 for a field emission and 100 for a Schottky emitter. And in all my years, I've not really looked into why, so I can't answer that question if it's posed. This is from Hitachi, so kind of showing the same thing I painstakingly drew, kind of showing that a thermionic gun is very similar, whether you're using a Lab 6 or this is tungsten, this is Lab 6. They have a different schematic for the Lab 6 because it's a single crystal that's coated. It heats up. Field emission, we have the double assembly. One thing a field emission doesn't have is a well net cap, and I'm realizing now I kind of drew this one a little incorrectly looking at this Hitachi diagram, so I apologize for that. But it's kind of more of a valve, though. It doesn't function as a well net. Showing the equations, so thermionic emission, the flux of electrons is directly proportional to temperature times this exponent function. So it's the work function divided by a Boltzmann's constant times temperature. So extremely temperature dependent. I go over this in other classes I've taught before. It's actually, I borrowed this from the book I used for that class, or used to use for that class. You have different constants, so the Richardson-Dushman constant, and you can swap that out for this effective emission constant. But the point of the matter is it's really dependent on temperature, the flux of electrons, and also the work function as well, but really temperature dependent. Schottky is also dependent on temperature, but now we're adding the electric field. So from the mathematical equations, we see that Schottky emission is also dependent on temperature, but now we're dependent on electric field as well. So it's a field-assisted emission is another way to refer to Schottky emission. Field-assisted tunneling and flux, there's no temperature, so we don't need to spend too much time looking at these equations, but these equations are there. So the flux of these field-emitted electrons directly proportional to the applied electric field. Okay, no temperature dependence at all. That's why it's called cold cathode technology. Kind of comparison of the characteristics of electron guns. I always like looking at tables, and if you look, we have different pressures for tungsten and lanthanum hexaboride, or the Lab 6, and it's different, right? So the working pressure, it's a little bit higher here for lanthanum hexaboride, so you can't just swap it out. And to my knowledge, there's not an instrument out there that's interchangeable. Maybe there is. I've not come across one, and I've actually asked. When I bought the instrument I bought, that 3500, I was actually looking for something that I could run a Lab 6 in, and because they are better. But there's two reasons you want to get this over a field emission. One is you don't have the quite the vacuum system necessity that you need on a field emission scope, and the other reason is you don't have to replace the filament quite as often. And so you see 1,000 hours versus roughly 50 hours for this. And this is a little off because I mean, I've seen field emission tips last a decade or more even. And I personally don't have that much experience with the Schottky emission scope. Um, Alrighty, I'm kind of taking a little segue here to explain something related to electron guns. And so if we take a look at like a simple circuit and we have voltage and a resistance, right? And I'm not really worried about polarity or anything, but we're all familiar with Ohm's law. And it's V equals I R. And so V is voltage. I, of course, is current. And R is resistance. I is resistance. Okay, so we have this circuit, and we can kind of visualize voltage is basically what pushes the electron, pushes resistance basically impedes the electron's movement. Impedes, I think I spelled it right. And current is basically the number of electrons. It's actually the number of electrons moving per unit time. And so if we have a little electron, and so this would be a really low current because it's only one electron, we could have voltage is basically pushing on it. It's supposed to be an arrow. I'm sorry about that. My bad. Resistance, say our voltage is relatively higher. Resistance is pushing back, and E, our electron, is the current, so number of electrons. And back here, kind of giving away my little secret I'm doing over there. Voltage is volts, generally. Current is amps. And resistance is ohms. And kind of looking at circuits here, if we say we have, you know, a 2 amp this means 2 amps of electrons are flowing through at any given time, okay? And that's kind of going to be drawing it wrong. But let's just call it a 2 amp circuit. So 2 amps of electrons. Yeah, that's fine. And how many electrons is that? Well, we have to remember that 1 amp It also equals a joule per coulomb, but 1 amp, I'm sorry, coulomb per second, excuse me. But 1 amp is 6.241 times 10 to the 18 electrons per second. So up here, if we say we have a 2 amp circuit, it's simply 2 that's a lot of electrons. So it would just be 2 times 6.241 times 10 to the 18 electrons. I'll go ahead and write it out per second. And let me get my handy dandy calculator. Should be better than that, but that's all right. 6.241 to the 18 times 2 is 1 point, I'm going to round it, 1.25. All right, so when we come over here to our electron gun, we have a beam current. So here's our electron beam. So this is supposed to be beam current. Maybe I shouldn't write it in cursive. So beam current. And SCMs, they're on the order of microamps. And let me write this in not so rainbow brighty. So SEMS in terms of microamps. So if I'm running my electron gun, and so typical beam conditions, let's just say 30 kilovolts of accelerating potential. And one would be kind of my spec, the spec of my machine. Let's just say 182 microamps of current. And I'm sorry, I'm writing really sloppy. Man, I apologize again. Sorry, I'm laughing at myself. Trying to deliver the best material possible here. 182 microamps of current. Well, how many electrons is that? Okay, well, we know what an amp is. And where did I write it? I wrote it here. So if we have 182 microamps, 1 amp is 6.241 times 10 to the 18 electrons. And I'm going to just, sorry, I'm just going to put it underneath us. So electrons per second. Trying to use my railroad track method. And 1 micro is 10 to the negative 6. And so let's work that out. So 182 times 6.241 times 10 to the negative 6. Oops, I messed up. I won't edit it out. I should, though. There you go. I got 1.14. 1.14 times 10 to the 15 electrons per second. If we go back, and if you remember, I talked about the XRD, and the accelerating voltage on an XRD is pretty similar. Okay, so an XRD X-ray tube and we said this has to be water cooled. And let's just say, okay, so before I go too far, each electron sees this 30 kilovolts. And an electron volt, we can convert that to joules. So we'll get back to this XRD thing right quick, but each electron sees 30 kilovolts. And an EV is the charge of the electron times the voltage. And so if we have 1.4 times 10 to the 15 electrons per second, and the elementary charge is 1.6 times 10 to the negative 19 coulombs. If we want to be specific, it's coulombs per electron. And a volt is a coulomb per second. So we can say 30,000 volts, and or we could substitute joules per coulomb. So 1 volt, we'll just work out all the units, is a joule per coulomb. So coulombs will cancel, volts will cancel, and electrons per cancel. So we're going to have joules per second, which is fine. Let's see. Oops. 1.4 e to the 15, or times 10 to the 15 times 1.6 e to the negative 19 times 30,000. So I got 6.72. Yes, that's right. The powers of 10. Oops. Didn't want to make that red. 6.72 joules per second. So that's how much energy is hitting the surface in a SEM. SEM at 30 kV with this beam current that we've said, 182. So let's go back. So we can look at an XRD and also I believe we talked about electron beam melters, and they're running with similar beam currents as well. So an XRD the tube needs to be water cooled, or you will melt the target. That's supposed to be an H. Or you melt the target. An electron beam melter, you want to melt, and it's similar beam current, so remember that. We're at about 20 kV on an XRD, but we're at about 40 milliamps. Okay, so how many electrons are hitting the target? Are hitting the target. All right, so we have 40 milliamps and 1 amp. If I can't remember my conversion, I have it written right here, 2.41 times 10 to the 18. Electrons per second. And I can kind of draw that in there if I want. Is 1 amp, and a milli is 10 to the negative 3. So we're 3 orders of magnitude more electrons. Well, actually 2, because we had a higher beam current on our higher number. We had 100. Anyway, let me just work it out. 40 times 2.41 e to the 18 times, oops, that wasn't what I wanted to do, sorry, 40 times 2.41 times 10 to the negative 3. So I got 9.64 times 10 to the 16 electrons per second. And if we want to figure out how much energy that is. And so I can use the similar calculation I did over here for my SEM. I can do the same thing for the XRD. And 9.64 times 10 to the 16 electrons per second, and 1.6 times 10 to the negative 19 coulombs per electron. And I'm going to go ahead and just say joules per coulomb this time. So we have, slowed down there, 20 kilovolts. So 20,000 joules per coulomb. That's a C, trust me. And so let's see what we get. 9.64 e to the 16 times 1.6 e to the negative 19 times 20,000. So I got 308.48. joules per second. So that's a lot more energy, and we're 2 orders of magnitude greater, right? Roughly 2 powers of 10. And I kind of gave it away a little bit because we said we had 2 orders of magnitude more electrons on the XRD than the SEM, and a similar number for another machine that uses an electron gun for an electron beam melter. so EBM, an additive manufacturing method. Alrighty, well here's just kind of wrapping up a little bit of math behind an electron gun. And electron guns have a beam current, and that's the amount of electrons exiting the gun. And we kind of tried to make an analogy with a simple circuit. The voltage, the accelerating voltage, is pushing the electron down the column, or the group of electrons down the column. And there's not really a resistance if you think about it. You're pushing it through a vacuum, and any resistance would be air molecules, basically. And so higher vacuum machines would have less resistance, but we don't really calculate a resistance to it. We maybe could if we knew the landing energy, and there is some instrumentation that catches that. But for now, just focus on kind of the operating conditions of a SEM, kind of understand how they're different than other things that use an electron gun, like an X-ray diffractometer or an electron beam melter. And you'll see that the energy of the beam hitting the sample surface or the target in an XRD is much higher than the sample in an SEM. And it's about this range, 308.48, or in the hundreds of joules per second, that also allows for the melting of metal powder anyway, in an electron beam melter. So enjoy this, and let's move on with the lecture. Okay, so in this little video within a video, I've opened up the electron gun on the 3500. You can see this retaining ring here, and then you can see this is the well net cap, and then this is the orifice, or the little aperture the electrons come out of. And in this video, I'm actually changing the filament because it burnt out, and I was remiss. I didn't actually get a good shot of the filament, which is why I showed that other picture from Ted Pella of that filament. And here I can turn the volume off, so it just literally unscrews. It's like screwing in a light bulb. The well net cap assembly, and hold on, I put the ring down there, sorry, let me pause it. This well net cap assembly has holes in it and stuff like that to kind of dissipate heat a little better, because you don't want to overheat it. This is in a vacuum. We kind of see this O-ring. Always wearing gloves to handle this stuff. In fact, I wear gloves every time I use an SEM. Why? Because carbon, the element carbon, is the great enemy of scanning electron microscopes. And you have a lot of carbon and oil on your hands, and it'll volatilize in the SEM. So always wear gloves when you handle your specimens, and when you use the SEM is my mantra. So here I'm just pulling it out so it plugs in, and then you see the two probes right there. You see the two probes down there? That's the filament. So that actually connects to the tungsten hairpin inside the well net cap. So in here, this is actually the base. So this is the pre-centered cylinder. So this is the actual filament assembly. The well net cap screws onto the filament assembly, basically. And kind of showing the probes. That's where it went into. And oops. So sorry. I'm going to make this mistake. The background's yellow because of fluorescent lighting, if you didn't know that. Showing where it plugged into, and then I'm trying to show here, this is the accelerator anode, and the accelerator anode actually gets covered with tungsten as well. So when you change the filament out, you have to clean out the inside of the well net cap, and you have to clean out the accelerator, or clean off the accelerator anode. So this unscrews as well. And they sell various polishes for this, but I actually use the alumina slurry that we use to make metallographic specimens in a little bit of ethanol. And so that's how I clean this stuff off with the Q-tip. And you can see at the beginning of the video I had the Q-tip in my hand already. I was kind of showing this, so I took the well net cap off, but I didn't show you. Oh, I did show the top. When I first looked at it, I couldn't see it because my eyes are not good. But this is the filament like we saw on the Ted Pella picture. The whole thing comes this way now, and it used to be, and I'll say this again, in the old days, you only got the little white part with the probes, and you had to center it in this assembly, and it took a couple of days, literally, to change it out. There was no jig or anything like that that you could make things a little easier. And so these come pre-centered from the factory. You put these two washers on to control the emission current. And so if you have the filament closer to the well nut cap, you'll get a higher current, but you'll also burn out your filament faster. And so these little copper spacers actually move the filament away from the well nut cap. And you're also moving it farther away from the accelerator anode as well. So I kind of previewed this by accident. So on the subject of vacuum systems, and we were talking about different vacuums. So that was kind of my segue here. Field emission using the highest vacuum. Low vacuum is 760 torr to 1 torr. Medium vacuum is 1 torr to 10 to negative 2 torr. A high vacuum is 10 to the negative 3 to right at 10 to the negative 7. So the 3500 runs at this range, 10 to the negative 3 to 10 to the negative 7. To use the hexaboride filament, I would need this. Okay, so ultra high, and extreme high vacuum would be used, right? So let's look at our definition. On 10 to the negative 7, I'm sorry, 10 to the negative 8. So 10 to the negative 8, I'm in ultra high. And this one's 10 to the negative 5, so I'm a little off. Okay, so let's just use this. So we're still at high vacuum. And so this is contradicting. I'm just realizing it's contradicting my other slide here. Didn't realize that. 10 to the negative 7 torr. So I'm going to go out on a limb and say these guys are wrong, because I've always been taught that the pressure for these hexaborides is actually higher, much higher than this. But it's still a higher vacuum. So whether I'm right or wrong, you still have to run hexaboride at a higher vacuum. How you get there? You get to the kind of lower vacuum, right? To this, or medium vacuum actually, with just a mechanical roughing pump. Diffusion pumps are what was used widely before the turbomolecular pump or molecular turbo pump came out. Okay, and I don't like them because they use oil, and so this was kind of an older style pump. Molecular turbo pumps have kind of replaced them. If you've ever used the the tabletop, you actually hear it rev up. And to get to 10 to 6 and below, you need an ion pump. So these field emission scopes are using the ion pump, whereas for sure the thermionics are using molecular turbo pumps because they can get all the way up to 10 to the negative 6 torr. And anywho, so different types of pumps. I won't go through these links just now, and we'll kind of carry on. So just know that there's different types of pumps. So mechanical pump, the rough pump, it's always the loudest one. You know it when you walk into the room. We've kind of done our best, particularly on the 4800, to move the rough pump to the kind of the old dark room that borders that wall. Diffusion pumps aren't really used that much now. It's pretty much mostly a molecular turbo pump. You'll find these diffusion pumps on older systems though. And again, an ion pump, we have this on the field emission. It ionizes gas, attracts the gas to the electrodes. So they're actually in the column. And I showed you those 3 valves on the 4800 schematic or picture. This is kind of showing where the ion pumps would be. A turbo pump would be down here. So and then the roughing pump is typically external to the system. Again, this is showing the pumps again. This is showing an older diffusion pump on this older schematic. But ODP, so oil diffusion pump, or TMP, which is turbomolecular pump. So nowadays it's been pretty much replaced. And oil rotary pump is the diffusion, the rough pump, and all the ones we have are using oil, or are oil rotary pumps. I'll let you kind of look through this. I always like tables, but I don't like reading them in lectures. And so you can pause it if you're interested in seeing kind of the differences. Um, and I always say I don't like it, then I read it anyway. I don't think. Yeah, here you go. Oil diffusion pump. So see, some dispersion of oil vapor. You can actually get oil into the chamber. Is kind of the big reason not to use a diffusion pump. That's the punchline I'll say there. But if you're interested in reading all the information, just pause it. Principal ray diagram. So we looked at this in optical microscopy, and it's a common misconception that a scanning electron microscope uses lenses to magnify. There are lenses in a scanning electron microscope. However, these lenses are used to actually control the beam shape, to actually focus the beam down. And this is an optical lens. This is an electric lens, basically. And so I got it from this Hackaday. Hackaday, great website. This individual is actually tearing down an old ISI. He got an old ISI somewhere, and he's rebuilding it. And these are the magnetic lenses in his old ISI column. And you go through different bores here, and it focuses the beam down. So you have an initial beam diameter coming out of the Wellnet cap if you're using thermionic. It gets focused down to a final beam diameter. And you try to preserve that beam diameter, that beam size with focus. The other thing you can control on an SEM is stigma, and that controls beam shape. Okay, and you do that with electromagnetic coils. On high-powered microscopes like a TEM, you generate a lot of heat with these coils, so you have to water cool them. In less powerful instruments like the tabletop and my 3500, you don't use water to cool the coils. Here's kind of the lens system. And so again, it demagnifies the electron spot, and I'm sure my face is over this piece of information. So I fixed it. And so lens system, it demagnifies the electron spot. So we have condenser lenses and objective lenses. And your final diameter is D naught, which is the beam size coming out of the Wellnet cap, times M1, M2, M3. These are demagnifiers, so you're going to be smaller. So D3 is always going to be smaller than D naught. Working distance, it's the difference between basically your objective and your specimen. So we've seen the term working distance before. Scanning coils, they actually control the raster of the beam, and they're another set of electromagnetic coils, very similar to what we've seen here. So notes on SEM optics, there's no magnification on the image side, only condensing system to focus and raster the beam, and magnification of the SEM image happens by digital image processing, okay? And we have our scanning coils, which again, big copper coils, they raster the beam, okay? So let's just say this is our specimen. We're rastering the beam on the specimen in R by R to create an image. If we're at low mag, we're scanning a larger area, so we actually have a higher voltage at low mag to those scanning coils. When we scan a smaller area, that gives us a higher mag, and we're actually lower voltage because we don't have to raster it quite so wide. You get your magnification now just by blowing up the electronic signal generated over your scanned area to your monitor, to your screen. And it can be your monitor, it can be your printout, whatever. But the magnification is literally calculated by the ratio of your raster length to the length of your screen. And I kind of pose this question. I used to be really into the voltage to the mechanics behind the instrument. How does voltage applied to scanning coils affect screen magnification? It's inverse, okay? So low voltage, high mag, high voltage, low mag, okay? And hopefully you can visualize that. Higher voltage gives you a bigger R, And your length of your screen is static, so a bigger R means lower mag. Low voltage means a smaller R, so your ratio of your screen to your raster R is bigger, so you get a bigger magnification. Okay, so magnification is just length of the screen divided by the length of the raster. That's all it is. And it's since you're generating an electronic signal by hitting your specimen with electrons, getting secondary or backscattered electrons, which in different ways are converted to an electronic signal, you can easily process it. My slide's telling me this is an outstanding place to stop, so I will stop now. We'll pick up more with kind of the mechanics of detectors and stuff like that in the next lecture. Hopefully I didn't go on too many rants and that this has been informative to you. And if you have any questions, as always, please feel free to let me know. Thank you very much. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.